hand sums, and I'm starting to feel pretty good about what you did there. Guys, in left and right hand sums, is it a good thing for units to match when we do areas of each one of those boxes or not? In other words, what I'm kind of asking is this. If I had a box to find an area to get maybe some kind of distance measured, if I had seconds down here and feet per minute right here, or I had hours down here and miles per hour right here, which bar would be a nice one to get us a distance measured? Top one or bottom one?
Bottom.
What's your reasoning for the bottom one?
Units are the same.
Yeah, because our hour units would do what to each other when we took a length times a width? And that will leave us with some kind of a displacement in terms of miles, right? Okay, now in this one right here, you might have to turn seconds into what, kids? Like a fraction of a minute. So 1 second would be what fraction of a minute?
160.
So you might have to change some numbers to say, okay, if this is just 1 second, you might call this 1/60th of a minute then for your distance and change things. But you've got to make sure units cancel and stuff like that. Guys, on 3.2 notes, we'll get started here. I wondered if anybody had any final questions on 151 at all. I think I assigned 1 through 11 on that. Was there anything you guys wanted to discuss there at 151? If you weren't here Friday, I let the class know that I put the solutions for chapter 3 online. Okay, so if you need to go there to the calculus webpage and look, you can see that stuff there. I think those solutions are good because they show the work involved with that too, don't they? Okay. All right. So any questions 151 before I get started here today? All right, my friends, let's talk here, guys. We're going to start talking about what's known as the definite integral today. Okay. We'll start talking about definite integral. This is going to be a key concept today, and I've got news for you. Moving forward with this stuff, decimals is going to help us a lot moving forward. So probably want to make sure you've got your Chromebook. Probably won't need it today, but I think moving forward as we continue to work on integrals, you're going to want to have Chromebook handy for decimals, okay? So guys, things that we're going to cover today. We're going to cover terminology and notation of integration, okay? Integration is kind of like a word we use. It's a process of finding an antiderivative. So you're going to hear the word integration a lot, okay? We're going to connect the definite integral and the area under a curve. We've kind of done estimates of areas under a curve with left and right hand sum, haven't we? Okay, so we're going to be looking at that there. We're going to talk about some rules for definite integrals, okay? The big one right here, put a star in this one, okay? Fundamental theorem of calculus, all right? We're going to look at how do you evaluate that there today, but that's going to be a big concept today. We're going to look at some antiderivative rules or some anti-differentiation rules, but just the what for now?
Basic.
Basics. We'll get into the stuff that's more in depth probably, maybe by the end of the trimester, but probably more so in third trimester. And then lastly right here, we're going to look at how do you find a definite integral with calculator. This calculator most likely, my friends, will be decimals for you. Okay. All right. Guys, it says in the preceding section, you estimated distances, areas, and volumes with finite sums. You guys remember the name of that guy? Started with an R.
Ronald.
Did you find what you needed there? Riemann sums. You remember that?
Yeah.
Okay, Riemann sums. So basically, when I say finite sums, we're kind of talking left and right hand sums. It says the terms in the sums were obtained by multiplying selected function values or data points by the lengths of their intervals. Okay, this was the process of finding the sums of left and right hand intervals. In this section, we're going to move beyond finite sums to see what happens in the limit. Okay, remember we talked about some of the end of the chapter 3, section 1, we said we can get a really, really, really good estimate of the area under the curve if the width or the interval length is really, really close to what distance? 0. So we talk about this idea, see what happens in the limit as the terms become infinitely small around their numbers, or maybe they're infinitely large. Guys, kind of what we're talking about is this. We're going to look at interval lengths where we have a limit as that distance x either approaches 0. Okay? This is going to be a big concept right here. All right, so it's kind of like saying down here on this interval length, this distance right here is going to be so close to 0 gonna be a value really close to 0 down there for that interval length. We wanna look at what happens there, because we had already said, the smaller or the skinnier I can make my bars, what was that gonna do to your accuracy of your estimate for the area under the curve? Was it gonna make it more accurate or less accurate?
More.
We said the skinnier the bars, the better we'd be, right? So we're gonna look at bars that are so skinny that that distance or that interval length is gonna be really close to what? 0, okay? All right, let's talk objective number 1. What the heck is integration, and what's it even look like, okay? You're gonna start to see some funky symbols, my friends. You're gonna see some symbols that's like, ooh, what is that? All right? Anybody ever seen this symbol before?
Looks like something that would be like music.
What's that?
Looks like something that would be in music.
Almost, yeah, it does, okay? Let's talk objective 1 right here, guys. Terminology and notation of integration, all right? It says the parts of a definite integral. Definite means we have, definite means we're gonna be finding the area from what to what?
A to B.
A to B along the x-axis. I wanna make it a little sketch here. Is that okay with you guys? Let's just make a sketch that looks like this. You might have a graph that maybe does something like this. Oh, that's good. Okay, we might have a little graph that does something like that. You might want to sketch this, totally up to you. Okay, so within this we might have a point here and a point here. Okay, and this point right here might relate to an A value down here. And this point right here might relate to some kind of B value. Nonetheless, A and B are on which axis? Okay, it's on the x-axis. Okay, so here's the deal. What we say here is this. We say the area denoted, or area everywhere in here, if I were to be able to shade that whole area like this, we say that this is gonna be some kind of total area right here. Now, the only way that we know how to find this area right now is left to right-hand sums. You guys agree with that? Okay. Well, we start throwing symbols in here like this. We say that this area is represented by, okay, this is how you read this. This is the definite integral where my lower limit is A and my upper limit is B of some function f of x dx. This whole thing right here represents that total area that would be shaded right there, okay? So let's just make sure we understand this. B is considered my what, kids?
Upper.
Because it's the value furthest to the
Right.
right. This is the symbol for integration. We use this kind of goofy looking S. You said it looked like a what again, Kate? Some kind of a,
Like a music thing.
like a music thing, okay? All right. So maybe we could sing a song when we do integration.
Oh, that's okay.
You don't want to do that? I'm a really good singer.
Let's hear it.
No,
Yeah.
absolutely not. Okay? I sing and dance, they're both the same. All right? Okay, lower limit of integration. What do you think the lower limit's gonna be here then? A. Okay, we call the function we're integrating the integrand, all right? Or the function right here that defines our graph right here, that would be f of x, okay? So this part right here, the graph, that's just this f of x. And then this dx right here tells us, and we've talked about this right here, this tells us the variable of integration. We're gonna find an antiderivative with respect to what, kids? X. If this was a dy out here, then it would have been with respect to y, okay? So it's just the variable of integration. So don't freak out when you see that. All you need to know is that this right here, this whole mess right here, really represents the total area in that curve, okay? That mess right there represents the total area bounded by this vertical line A, this vertical line B, the x-axis, and this right up here. That whole area right there is defined by that mess, okay? So think of seeing definite integrals as a what? Total area, okay? All right, so are you okay with what this stuff means right here first? We good there? Okay. Then the next part right here, guys, we're going to look at the definite integral on an area. So again, area under a curve, and kind of like we just talked about up there. So definite integral and area. By definition, the definite integral is an area under a curve as defined by a definite integral. So right here, it says if y equals what? Is what?
Non-negative.
Non-negative, and this is a word, weird word. I almost said word weird. word?
Integrable.
Over a closed interval a and b, then the area under the curve, y equals f of x from a to b is the integral of f from a to b. Okay? You're going to see a lot right here. This is really saying the same thing right here that we talked about. If I have a function, f of x, that we're going to find an antiderivative or integrate with respect to what variable? X, where the lower limit is what?
A,
And the upper limit is what?
B.
Then that's going to equal sum total area A. Just understand that this mess really means it's sum total area. Alright? Note, you can use integrals to calculate areas, and you can use areas to calculate calculate integrals. But you can only do that when the areas are what?
Easy to find.
I'm going to do something up here. Kids, over here on the right. If this was a graph right here, this was A, this was B, would this area under the curve be easy to find?
Yeah,
Why?
it's a triangle.
It's a triangle, right? We know area formulas for certain shapes. Sometimes the graphs that are produced from f of x are going to give us a specific shape, in this case a triangle. But what about this, my friends? Is there a formula for finding the area under the curve like this? No, but guess what? We are going to find a way to find that total area under there using antiderivatives, okay? So it's a note down there that says you can actually find the integrals to calculate areas, and you can use areas to calculate integrals typically when they are easy to find. There's a lot we need to learn yet in order to find areas like this relative to antiderivatives. We'll get there, but right now we want to make this kind of simple so you understand concept going on here, okay? All right, so knowing this right here, knowing that this mess is really the area under a curve from where to where, lower limit
A,
to upper limit,
B.
is equal to some area. Let's see what's on the next page here. Hey. Oh, why is my next page blank?
It's just this one line for us.
It's alright though. Your example.
Let me see that.
There's like another blank page.
Is that on the last page? Okay, so I'm not sure.
I
I bet
think
I
it
know
just-
why. I bet I know what happened. I had typed this in Google Documents, and then I moved it over to a Word form. I bet it moved some things around a little bit.
Yeah, there's-
Okay, no problem. Well, let's just see what's on the next page. Guys, that page was easy. Very good. Are you here? Is that what you have next there, my friends?
Yeah.
Okay, let's talk some examples right here. Okay, so here's the deal. We're going to use the graph of the integrand and the areas to evaluate the integral. Okay, so right here, kids, this says find the definite integral from lower limit of what?
1,
To what?
5,
Of a function which is just what?
6.
Okay, so I'm going to kind of talk about this. Our function right here, I'm going to highlight our functions in this, okay? I'm going to highlight our functions right here. Oh, that's kind of bad. Okay, so here's our function, 6, okay? If I asked you to graph the equation y equals 6 or f of x equals 6, what would that graph look like?
F of x, it would just be a straight line.
It'd be a straight line. Actually, on the on the y-axis, we would go up to what value? We're gonna go up there to 6, aren't we? Okay, so this is the x value of 6, okay, or this is like the line y equals 6 right here. That's our function we're dealing with. That would just be a horizontal line crossing the y-axis at 6, right?
Mm-hmm.
If it was y equals 19, it would just be a horizontal line crossing the y-axis at what value?
19.
Okay, this here says we're looking to find the definite integral, so we're trying to find somewhat here, kids.
Area.
Okay, trying to find some area, so we're looking for the area under the curve. What is this again?
Y equals
What's your lower limit?
1.
1. What's your upper limit?
5.
So think of it this way. Isn't this 1 right down here, kids?
Mm-hmm.
Isn't this 5 right here? So graphically looking at this right here, for an upper limit of 5, look at the graph at the right. You have a lower limit of 1 and an upper limit of 5. Now keep in mind the x-axis is part of our boundary line. So our boundary lines are those vertical lines at 1 and 5, the x-axis and that line y equals 6. If I look at this area under the curve bounded by x equal 1 and x equal 5 down to the x-axis, what shape is formed?
Rectangle.
It's really a rectangle, isn't it? Talk to me about this rectangle that we get. What's this interval length from 1 to 5?
4.
It is 4. Talk to me about the height of that rectangle.
6.
My friends, the integral from 1 to 5 of the function 6 with respect to x is equal to what value? 4 times 6 would be how much?
24.
Okay, because what shape was formed here again, kids?
A rectangle.
A rectangle. We can just do simple base times height stuff here, can't we? All right. All in agreement there right now? Awesome. I want you guys to try part B on your own. I'm curious to see what you get, okay? So in part B, it says find the definite integral from lower limit of what?
2.
To upper limit of
5.
what function?
4.
Okay, you guys agree 4x is like a line that starts at the origin, because at 4x would be 4x plus 0, right? Okay, the origin, oh my gosh, this is not the best graph in the world. We'll make it, I better help you with this, is that okay?
Yeah.
Yeah, I think you should.
Not sure I like this graph that's being used here. Okay, this would be the function 4x right here, right, kids? Okay, what's your lower limit of? Let's call this a 2. Let's call this a what?
5.
Guys with me on that? Okay. Guys, if I let x equal 2 right here, what's the height of this point? Forget these numbers over here. I don't know why those are over there.
Oh.
Just forget
So-
those. They're not there. And the numbers down here, they're not there. Okay? Forget those. You don't see those. And if you do, your eyes are too good. You need to get a little older like me.
So would that just
Crop
be,
that out a little bit better the next time you make notes.
is it, so would it just be 1 or
Yeah, because if I plug, what's the function that we're working with here, kids?
4x?
4x, right? So if this is the function 4x, if you plug x equal 2 in, what do you get for an output? What would 4 times 2 make?
8.
So isn't this up here 8 units? 2 comma 8?
Oh, yeah. So the numbers are the same.
Maybe they are, I don't know. I'm gonna put the right ones in for sure, is that okay?
Yeah.
What if I plug 5 in, my friends?
You get 20.
So we all agree at this point up here it's 4 comma 20. Yeah, that would 4 comma 20.
Wait, 4 or 5?
Or 5 comma 20.
Yeah, 5 comma 20. That's the first mistake I've made all week.
We start Sunday.
I gave a test first hour. I don't think I made any, well, I'm sure my wife thinks I made mistakes yesterday. She gave me a fruit salad hat. Well, actually, my daughter made a fruit salad hat for me for my birthday. Have you heard this story yet, guys?
Yes.
Yeah? Did I
Yeah.
tell you this already, the fruit salad hat thing? Yeah, apparently there's like a Bert and Ernie meme that Ernie's wearing a hat, it's got fruit all over his hat, and he said, Bert, if I come up and you say rutabaga, 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 rutabaga 100 times, does that annoy you? And Bert's like, yep. So Ernie starts saying a different word. But my wife sent me a message one day that said, this is you annoying us all the time. Okay, so then Lucy thought it would be funny to make a fruit salad hat for me. And she said, anytime you're annoying, you have to wear this. And I said, that might be a permanent fixture on my head then. You guys ready to find this area?
Yeah.
Okay. The integral from this function right here, let's write this down. The integral from 2 to 5. Now guys, geometrically, is it possible to find the area of that shape?
Yes.
Yeah.
Because really it's what shape? It's like a triangle and rectangle. You can break it down that way. Or it's actually a trapezoid too, isn't it? If you remember your area formula for a trapezoid. Well, let's break it down into an area of a rectangle and a triangle. Is that okay with you guys? So, this rectangle in here, what's the interval length down here?
3,
3, and what's the height?
8.
So So this will be 3 by 8, won't it?
Mm-hmm.
Okay, and then this triangle right here, we have to be careful on this.
3 by 12.
It's 3 by 12, but since it's a triangle up top there, we should cut that in.
Divided by 2.
Okay, y'all agreed there? You know, again, I can get away with these because we have formulas for geometric shapes when the graph is formed from some function. So I would say the antiderivative, or the definite integral from lower limit 2 to upper limit 5 of our function, which was what?
4x.
4x. We're trying to find that value, or that integral, with respect to x would equal, okay, how about this bottom rectangle value? What's that going to be, friends?
24.
Plus, how about the triangular part there?
18.
18, yep, 3 times 12, or yeah, divided by 2 would be 18. Guys, I'm coming up with 42 here. Okay?
Would you put units on these?
You could call it square units, and I'm gonna be honest with you, Ellie, the units are gonna start to happen when we start getting the more application problems. So when we start looking at like a real life problem that's gonna say, oh, the amount of money you earn each day is, at a company is defined by this following function. How much money did you earn on the 12th day or something like that?
Okay.
Then yes, units will start to matter for you. But as of now, you can just put 42 square units up there since we understand that we're looking for an area, okay? So those units will have, and kind of like what we did here, this unit right here, if I multiply it over here, miles per hour for a height times the interval length of hours, what unit would that bar possess right here? If I took this times this, what would the hours units do? And the area of this bar would be in terms of miles then. So we'll start attaching units to that to make that happen eventually, yes. Okay, great question. Guys, how are we on that example?
Oh, fabulous.
Good so far?
Good.
All good? Gnarly. Oh my gosh. Guys, what happens then if a function is non-positive? Meaning it travels where?
Below the x-axis.
Okay, in this case, the integral is what?
0 to 5.
Okay, this is an interesting one. I'm not sure that's right. I want to check something here quickly. I think there's a typo in this. Let me check something real quickly, would you? This should be a 1 up here, friends. Okay, change that to a 1. Where it says 2, that should equal 1. Okay, you guys with me?
Yes.
So, guys, now what happens here? Here's the deal. Guys, think about your heights. Any height above the x-axis is considered what kind of a value?
Positive.
It's considered positive, right? Okay, and then any height above the x-axis, or I'm sorry, below the x-axis would be considered what?
Negative.
Negative. So when we start talking integrals right here, it's possible that area could be what kind of a value?
Negative.
Negative. And that's going to happen right here when your area goes below. So again, the x-axis is crucial for us in terms of doing integrals right here. But when I'm looking at areas where graphs travel above the x-axis and below the x-axis, some goofy things start to happen. So you guys have changed this to 1. Okay, it says given that the area, what's your lower limit?
0.
What's your upper limit?
5.
That's equal to what value?
1.
Okay, so right in here, it's right in here, this area, that's right in here. This area is right in here. 0 to pi is right there, isn't it, friends?
Mm-hmm.
So if I would shape that whole thing in, that area is positive 1 right there. That's 1 square unit inside of that, okay? Now the next question begins, well, What if we wanna find the total area from 0 to what?
2x.
Okay. Upper limit would be what here?
2x.
2 pi,
Oh, 2
right?
pi, my
Of the same function though, right?
Yeah.
Okay, so we've gone from 0 to pi right here, we know that's 1. What do you think then, I've got to include this area right down here. I've got to include this area right down here. Belle, don't get excited that I'm using red and yellow together, okay? I'm not changing. What do you think that area is down there? It looks like the areas are exactly the same, right? But since one region lies above the x-axis, that would be considered an area of +1. Okay, so how about the area below the x-axis? What kind of value is that gonna hold then for area? -1, yep. Okay, so you're talking about areas relative to being above and below. Okay, anything that's below the x-axis is gonna take on an area of -1. And think about it this way. Think of my left and right hand sums this way. I'm gonna draw a little box over here. Pretend right here that this is the x-axis. Let's say I have a bar that does this. Maybe it's 2 by 4 right there, okay? Basically, it's got an interval length of 2, and what's its height, guys? 4. When we start counting height relative to the x-axis, maybe this interval length is 2, and this is -5 this time, okay? Those heights are what we're gonna have some kind of a positive or negative value to, okay? The intervals, you can always move left to right and count positively, but guys, what would the area of this be right here?
The 8.
8. What would this area then really be?
-10.
Okay. So guys, when we do integrals, we've got to account for that right here. So the question becomes this: what do you think the integral is starting at 0, so right here, and then going all the way over to 2 pi? What do you think the definite integral value is going to equal for that?
Is it gonna be 0?
It's going to be 0 because these two areas kind of do what to each other?
Cancel.
Cancel each other out. So this is actually going to be 1 plus -1, which is going to get you that value of 0 there. Okay?
Or is that like, should you put in 1 plus -1?
You could, not, eventually you're gonna start seeing this enough, Ellie, that you're gonna be like, yeah, I know that's 0 now. I want you to understand why it's 0 there, okay? Because the way I should have probably written this is it's the integral from 0 to pi plus the integral from pi to 2 pi right here. That make sense to you?
Yeah.
So you could just say it's 0, but visually I put the 1 plus the -1 up there to understand that these two do what to each other then? Take each other out, don't they? Okay. All right. Are we on to the next page, friends?
Yeah.
Awesome. Let's take a look at the next one here. Any questions for me so far? Or is this making pretty good sense so far? You with me right now? Yeah?
Yeah.
Awesome. Okay, let's look next page here. Maybe we can make things more difficult.
Oh my god, why are you wasting so much paper?
I don't know. It copied funny. I'm so sorry. Do you forgive me?
I have to think about it. The trees.
No, it's okay, because I thought the notes
Well,
were gonna be
I
really
brought
long.
more trees into the room because I thought you wanted fresher air. I was thinking of you guys. But they still have a half-life. So how can
Let's
they
not
be
talk
dead?
about half-lives here.
Oh god.
Ellie, you said that like you were almost angry about it.
Hey, I actually liked those. That
Yeah,
was
they were
way
good.
better than this.
Oh, you think so? See, I really like this stuff.
This isn't bad, it was last.
I know, it's a lot of work. Okay, guys, write a note to this, whatever, however you wanna do this. This is some big time important stuff here, okay? Normally I wouldn't start showing you this stuff till later on in a different chapter, but I think we might as well get rolling with it right now, because the more I can give you shortcuts and make them relatable to what we're really doing here, I think the better you're gonna be at this stuff, and I think the more successful you'll be moving forward. So, our notes aren't gonna match exactly some of the things that are in the book in 3.2, but I think you're gonna find that, what I've given you is actually more than what we needed to give you to be successful and save some time with this. So, let's get rolling right here. Objective 3 says rules for definite integrals, okay? My friends, look at order of integration right here. Okay, what's your lower limit right now?
B.
What's your upper limit?
A.
Okay, it says if I ever have, an antiderivative or a definite integral from a lower limit of b to a of some function f of x, that's gonna equal, okay, the thing I want you to notice right here is this. What did I do to my limits on the right?
You flip them.
Instead of a and b here, they got what?
B and A.
They got flipped, okay? So this area, if this area right here equaled 17, I'm just gonna say, maybe this area was 17 for a value. Then what would this integral be then? Would have been negative 17, so the way I keep them equal is to throw what sign out here?
Negative.
A negative sign. Does that make sense to you? So if I switch these around, what do I have to throw out in front here?
Negative.
A negative sign. Does that make sense?
Mm-hmm.
So order of integration says this, if you switch the limits, if you have a on the bottom and b up top, if you switch them, and you wanna keep equality, what sign do you have to put in front of the, integral sign?
Negative.
A negative sign, okay? So here's what I would tell you, now I'll give you an example, so if it was like the integral of 7 to 12 of some function f of x, this would equal the negative integral, what are you gonna do then?
Of 7 and 12.
Okay, are you with me there? Okay, know that one, alright? Guys, the zero integral is easy. If you ever have a zero integral, so here's the deal, what do you notice about your lower limit?
It's the same as the
If you ever have a lower limit and an upper limit that's the same, do you have any interval?
No.
The lower limit and the upper limit are the same, so there's no width to it, right?
Right.
So 0 times whatever height you have on the function is gonna give you what?
0.
So if this one here, the 0, 1, it says, I'm just gonna make a note, upper and lower limits are the
Same.
upper and lower limits are the same. Okay? I like this next one, constant multiple one. Okay? Constant multiple says this, if you have a lower limit of a times b of some constant k times a function, remember that 4x one we just did?
Yeah.
4 would have been like your k value. You could have taken that 4 according to this rule and moved it where?
Front.
Out to the front. So we had the example already. What were the limits on that one? Was it 5 to, or 2 to 5?
Yeah.
I'll just write this down again. We could have said this, we had to evaluate one area-wise, and it was the integral from 2 to 5, I think, was it 4x was that function?
Yep.
This would be the same as, okay, 4 times this function x right here. You know, if I could factor something out of a function right here, that's the same as 4 times the integral from 2 to 5, it's just the function x. So if you can factor some constant value out of your function, so like right here, if I had this, maybe I was doing the integral from 0 to 6 of 3x squared plus 9x plus 6 right here. Guys, what common factor could I take out of each of these terms?
3.
That would be the same as 3 times the integral from 0 to 6 of x squared plus 3x plus 2 like that. Okay? Does that make sense?
Yeah.
Okay, so I can factor something out. Okay, so on this constant multiple one, I want you to really think to factor something out. Okay, so I'll make that little note there. Okay, and then the next two are pretty much straightforward here. This here says sum and difference. So if you ever have a function f plus a function g and you want to know the integral of that, or the area of that, you can break it down into two integrals. It would be the integral from a to b of what function first,
After that.
plus or minus whatever sign is in here, the integral from a to b of your function g of x. So if I really wanted to, kids, I could turn this into the following up here. This top one, I'll get rid of this here. If I wanted to write this one down, isn't there a bunch of addition going on in my function here?
Yeah.
This could be the integral from 0 to 6 of 3x squared plus the integral from 0 to 6 of what?
9x.
Plus the integral, and I don't know why you would do this, but you could. You alright with that? Just know that these mean the same thing, so right here, sum and difference right here. And then there's an additivity rule, which says if I have an integral from a to b, and I'm gonna make a sketch of this one in terms of what's going on, of a to b of a function plus, what do you notice about your limits here?
Well, the upper of the other one is the lower of that
Okay,
one.
so let me kind of give you a sketch of what's going on here. Yeah, we're going from A to B, and then from B to C. It's like you went from A to B to C, so that totally is like going from A to what?
C.
Yeah, so this one here says if you have a function, and I don't know, maybe your function looks like this. Maybe here's A, here's B, and here's C. Maybe they broke it down to two parts. They found the area from A to B, and then they found the area from B to C, and then to get the total area, they did what with it?
Added them together.
Mm-hmm. So this is like the integral from, and I'm not gonna put all the stuff in there, but this is like your integral from A to B, and this is like your integral from B to C right here. That would equal the total integral from, what's the absolute furthest left point,
A,
and what's the furthest right?
C.
So what you're kinda looking for, in this one right here is the following. You're kinda saying, hey, if the upper limit of one integral matches the lower limit of another one, then that means they're two right next to each other. Put them together as one. Okay, put them together as one, all right? You want me to blow that up so you can see that a little better? Hang on a second. Can you see that better now?
Yeah.
Okay.
Is that
Kids,
A on the bottom one?
That's an A to a B and a B to a C. So this goes A to B, this goes B to C. That's gonna equal the total integral from A to C, the two together in there. Is that what you were wondering there, Kate?
Yeah.
Good with that? Okay. My friends, I think knowing that right there, first question for you, do you have that stuff written down? My question. Okay. I think this would be a good place to stop today. I'm not gonna give you an assignment. We're not completely done with this yet, but I feel pretty good about what we're doing here today. So let me stop this here.
Oh, there's nothing